Now let us see what are the applications of ESR spectroscopy. There are some applications. The first one, nuclear spin and hyperfine splitting. Now the presence of a nuclear spin, if the nucleus has a spin I, then our ESR energy level will split up into 2I plus 1 components. That is the presence, if there is a nuclear spin, then ESR line split up into 2I plus 1 components. And this implies that analysis of ESR spectrum will give the information about nuclear spin. If the ESR spectrum has a hyperfine structure, then by observing the ESR spectrum we can determine the nuclear spin. This is the first application. Then the second one, structure of free radical. We can determine the structure of radical using ESR. So let us see what is meant by a radical. Radical means atoms or molecule or ion, anything that has at least one unpaired valence electron, that has at least one unpaired valence electron. If an atom or molecule or ion that has at least one unpaired valence electron, then we can say it as a radical. Simply we can say that free radical contains free electron. So ESR is used to determine the structure of free radical. Let us consider an example of CH3. Now it can be tetrahedral its structure can be a tetrahedral or planar, but ESR analysis shows that its structure is planar. CH3 is an example of free radical. From the geometry of CH3, it can be either tetrahedral or it can be planar. but CH3 is a free radical, that it has a free electron, so that there are the electron with unpaired spin. So we can use ESR for structure determination, and ESR shows that CH3, the structure of CH3 is planar. Then the third example is spin labeling in biomolecule. Spin labeling in using ESR, we can determine chemical and kinetical property, chemical and kinetic. Using ESR, we can determine the chemical and kinetic properties of biomolecule. Yes, we can determine the chemical and kinetic properties of biomolecule. As the process is, we are attaching a particular radical to a portion of biomolecule. The process of spin labeling is done in the following way. First, attach a particular radical to the portion of a biomolecule. We know that radicals are ESR active. So to determine the chemical and kinetic properties of biomolecule, first you have to attach a radical to the particular portion of the biomolecule. Now, and after that, study the environment of that biomolecule. You can study about the properties of that biomolecule with the help of that radical. And in the next step, study the environment. With the help of ESR radical. With why we are attaching the radical? Because radical contains free electron, so it is ESR active. So to study about a particular biomolecule, first you attach a particular radical to the particular portion of the biomolecule, and then study the ESR of that particular radical. Then we will get the information about the chemical and kinetic properties of the biomolecule. Then the fourth point, study the symmetry in crystal. We can use ESR to study the symmetry. Then the fifth point, spectroscopic splitting factor. Spectroscopic splitting fact. Here we can determine the G value of the unknown sample. For example, G0 is the G value, that is the Landé G factor G value of a standard sample. Then G1 the G value of unknown sample. Then we have G0 by G1, this is equal to B1 by B0, where B0 and B1 are the field required to resonance, field required for resonance in the two cases. So if we know B1 that is used to resonate the unknown sample, and B0 is the field used to resonate the known sample, then we can calculate the ratio of G0 by G1 from B1 by B0, and from that the G value of the unknown sample can be determined. These are the applications of ESR.